In this video, we're going to talk about suggested homework problems from 4.3. We're going to continue our discussion of area under a curve, but we're going to use definite integrals now to talk about that instead of our summations. And the formal definition of the definite integral is in the section, but we're not going to talk about any homework problems with that. You should look at that though. I've already kind of alluded to that the definite integral of a to b of f of x dx is equal to the limit as n goes to infinity, the summation of I equals 1 to n of f of ci delta x, where delta x is equal to b minus a over n, and ci is equal to a plus I delta x is a very good definition. Really, ci can be any anything that's within a to b, any amount of slices there that you want, that don't have to all be the same size. There just needs to be a pattern to them, but this is using those right endpoints of those rectangles will be helpful. We don't always have to use rectangles. We'll come back later with some other rules, and we could use things like trapezoids, and we could use other shapes, like in something called Simpson's rule, we can talk about little parabolic pieces that follow the curve a little bit better and give us less air and things like that. So, but we usually use rectangles because when we're squeezing out all the air, the formula for the area of a rectangle is the simplest area formula that we know. The properties for definite integrals will all follow the properties of the indefinite integrals that we talked about from 4.1, and those properties are restated here in 4.3, so you should look at those. And we also have the fundamental theorem of calculus, and it says that the definite integral from a to b of f of x dx means that I want to find the antiderivative of f, and I want to evaluate it from a to b, and that is antiderivative of f at b minus antiderivative of f at a. There's also another part of the fundamental theorem of calculus. It's kind of strange looking, but I promise you that you'll need to know it at some point, that says that if I take, and this can be any constant. I'm going to put 0 down here, but I'm going to tell you that this can be any constant to x of f of t and dt, and I differentiate this when I'm done with respect to x, that's a way to define the function lowercase f of x. Why does that one work? Because if I take the derivative with respect to x of capital F of t evaluated from 0 to x, that's derivative with respect to x of capital F of x minus capital F of whatever this constant is. That this whole thing here is a constant. And then when I take the derivative of the antiderivative is the original function. And then that's going to be minus 0, whatever this is. It's going to give me 0, and that's going to give me my original function f of x. So sometimes there's some non-elementary functions that the only way that we can represent their answer is to say that the indefinite integral of f of x, here, if I take this over to the other side, is equal to that's the only way to represent the answer for the indefinite interval sometimes, is really what this theorem is getting at. And so again, hold that one in your memory banks. You may see it on your test. You will see it later in classes like differential equations. So it's covered in this section of the textbook. But let's get to some of our questions from homework now. If I have f of x is equal to 5, and I have it, here's the picture that gives me the region from 0 to 4, I can write that area as 0 to 4, 5 dx. I have number 17. We have negative 5 to 5. And our f of x is 25 minus x squared dx. And then 19 is 0 to pi over 2 cosine of x dx. Then we'll look at 25. We'll actually do a little bit of arithmetic. These are going to be functions that I can draw a picture for, and it gives me a geometric region. So the whole point of this is to not do the calculus, but to do the geometry to get the same answer. So here's y equals x. We're going from 0, 0 to 4, 4 on the graph. This is a 90-degree angle. I'm talking about this area of this right triangle here. So my area is 1/2 base times height is 2 times 4 is 8. And for 31, which is also in this section, I would not be able to do this with any integration formula that I know right now, but I can definitely look at the region there. Say that this is the top half of a circle of radius 7. So that area is going to be 1/2 of pi r squared. So that will be 49 pi over 2. Let's look now at 41, where we're going to use some integration properties. So part A asked me to find the integral from 0 to 7 of f of x dx. And so I'm going to split that integral into 2 smaller pieces. But the whole is equal to the sum of its parts here. I want to go all the way from 0 to 7. I can go through 5 and go from 0 to 5, and then 5 to 7. Just take this in 2 steps. And I know that this is 10 and this is 3, and that gives me an answer of 13. As long as the function is defined over the entire a to b, there's no like vertical asymptotes and things like that in between, we're good. And we assume that's the case here. Now, when I have an upper limit that's smaller than a lower limit, I just put a negative sign outside and change my limits. And so this is going to be a negative, and 0 to 5 is 10. C is 5 to 5 of f of x dx. So I have no width for my area, so I have no area. And if you want the work for that, that is going to be 5 minus 5. No, there's no work for that because I don't know what f of x is, but it's capital F of 5 minus capital F of 5. Anything minus itself is 0. I guess that's the work I can show for that. 0 to 5 of 3 f of x dx is equal to 3 integral 0 to 5 of f of x is 3 times 10 is 30. All right, moving right along now to our final problem for this video will be 47. And we've got regions that are under the curve and they'll have negative values for the definite integral, even though we've been talking about the definite integral as area, and area is always positive. If that area is under the x-axis, we'll put a negative sign with it for directionality. If it's above the x-axis, it'll stay positive. So for this is 47, part A, we go 0 to 2, f of x dx. So 0 to 2 is this quarter of this circle. And I need a negative sign since it's under the x-axis. Pi r squared, a negative 1/4 pi times 4. 4's will cancel and give me an answer of negative pi. For B, we have negative 4 to 2 of f of x dx. Negative 4 to 2 is two different shapes. I'm going to break up from negative 4 to negative 2 plus negative 2 to 2. And how did I say that? This is supposed to be 2 to 6. Not on that problem yet. I'll get to that one in a second. 2 to 6 is this triangle piece right here. So that's going to be 1/2 base, which is 6 minus 2 is 4 times my height, which is 2. 2 times 2 is 4. C, this is the one I was just talking about that I'm going to do in 2 pieces. So that's negative 4 to negative 2 f of x dx plus negative 2 to 2 f of x dx. And this is 1/2 of my base is a width of 2 here. My height is a width of 1, and this is negative. And then I have a negative pi, negative 1/2 pi r squared. This is a semicircle, it's 1/2. So this is negative 1. And then this is minus 1/2 of 4 pi is a negative 1 minus 2 pi. And it'll be helpful to me later to think of that as the opposite of 1 plus 2 pi. Scroll up here. D is -4 to 6 of f of x dx. So this is going to be -4 to 2 f of x dx plus 2 to 6 f of x dx, which are the last two problems that I just did. So this is a -1 minus 2 pi plus, and then 2 to 6 was 4. So this is 3 minus 2 pi. And E changes that up a little bit and says -4 to 6 of the absolute value of f of x dx. So that's going to be equal to the absolute value of let's see, -4 to 6 absolute value of f of x dx plus let's say -4 to 2 and then plus 2 to 6 absolute value of f of x dx. So if I take the absolute value from part C, I get 1 plus 2 pi, and if I take the absolute value from part B, I get 4, and I add that together, I get 5 plus 2 pi. And our last question here for part F is -4 to 6 of, and then these are brackets, plus 2, like that, is going to give me -4 to 6 f of x dx plus 2 integral -4 to 6 dx. The -4 to 6 f of x was right here, was 3 minus 2 pi plus, and then this is 2 times 6 minus a -4. It's one of my properties that when I have just integral of dx, that's x evaluated in these, so I can find the difference between the x values. So that's 6 plus 4 is 10. So that's 3 minus 2 pi plus 20 gives me 23 minus 2 pi for my final answer. So that's it for this video. We'll come back next time and we'll talk about suggested homework problems from 4.4. See you for the next video.